Hey there, and welcome. You ever just look at a piece of modern tech, a new building, or even some high-tech gear and just think, how on earth did they do that? So much of the world around us feels like it's straight out of science fiction. Well, today, we're going to pull back the curtain on one of the coolest bits of science hiding in plain sight. All right, let's just jump right in with a kind of wild question. Think about that shimmering, iridescent color on a butterfly's wing, or maybe on a high-efficiency solar panel. What if I told you that color was made with absolutely no pigment? No dyes, no paint, just structure. Just by shaping a surface so precisely it can literally play it tricks with light. How is that even possible? Well, the secret, it lies in the world of nanotechnology. We're talking about creating coatings on surfaces that are so incredibly thin, they're almost imaginary. These are called thin films, and they're like the invisible architects behind some of the most advanced materials that we use every single day. So the big question is, how in the world do you build something you can't even see? Well, the main technique, the foundation for all of this, is a process called chemical vapor deposition. You can just call it CVD, and trust me, it's every bit as cool as it sounds. Okay, so what is it? At its heart, CVD is basically a way of growing a solid coating onto a surface, literally atom by atom, by using a gas. I mean, imagine you could paint with vapor. That's kind of what we're doing here, just on an unbelievably small scale. And when I say small, I am not kidding. The films we make with CVD are measured in nanometers. Now, to give you some perspective, a single strand of your hair is about 100,000 nanometers wide. So we're talking about layers that can be 1,000,000 times thinner than that. It's this insane level of precision that gives these coatings their superpowers. So how does it all work? You know, the best way to wrap your head around the whole CVD process is to think of it like you're baking a cake. A very, very precise, high-tech, microscopic cake. You need exactly the right ingredients, the perfect temperature, and flawless timing. So, let's walk through this recipe step by step. First, you add your ingredients. These are special gases we call precursors, and you pump them into a sealed reaction chamber. Then, you heat up the oven, which brings the surface you're coating, we call that the substrate, to a super specific temperature. And that heat, that's what gets everything going. It breaks the gases apart and triggers a chemical reaction right there on the surface. And just like that, you've baked on a perfectly uniform, ultra-thin solid film. Now, of course, any master baker will tell you the secret is in the details, right? The final quality of your film, how smooth it is, how dense, what its special properties are. It all comes down to having absolute control over these key things. The temperature, the pressure inside the chamber, the way the gas flows, it all has to work in perfect harmony. You tweak one of them just a tiny bit, and you could get a completely different result. It's this really delicate dance between chemistry and physics. And just like with baking, there's more than one recipe. Traditional CVD needs a lot of heat, really high temperatures. But there's another version called Plasma-Enhanced CVD, or PECVD, that is super clever. It uses an energized gas, what we call a plasma, to give the reactions a little kickstart at much lower temperatures. And this is a total game changer, because it means we can put these incredible coatings on things that can't take the heat, like certain kinds of plastics. Okay, so that's the science, that's the how. But why does any of this matter? Let's get to the really exciting part, seeing how this invisible science creates a very visible impact in our world. We're going to dive into 3 incredible superpowers that CVD can give to completely ordinary materials. We're talking about creating color from pure light, building smart windows that literally adapt to the weather, and even designing surfaces that clean themselves. First up, structural color. This one is a real mind bender. See, the color you're used to from paint or dye works by absorbing light. A red t-shirt looks red because its dye absorbs every other color except red, which it reflects back to your eye. But structural color is totally different. Instead of using chemicals, we use CVD to build these tiny, tiny nanostructures, little ridges and grooves that physically mess with light waves. They bend light, scatter it, and make waves cancel each other out. The color you see depends entirely on the physical shape of that surface. It's color made from physics, not chemistry. And what can you do with this? Well, check this out. We can use CVD to put these vibrant, colorful coatings on solar panels that are designed to be part of a building's structure, and it doesn't really hurt their efficiency. So suddenly, architects can design these beautiful, colorful buildings that are also generating their own power. The whole building becomes a functional, beautiful power plant. Okay, next superpower, smart windows. And to get this one, there's one key term you gotta know: thermochromic. It's a fancy word, but all it means is a material that changes what it does when the temperature changes. Simple as that. So, by using CVD to lay down a super precise thermochromic film, we can create these amazing smart windows. On a hot summer day, the coating reacts to the heat and changes its structure to start blocking infrared light, that's heat, which helps keep the building cool. But then, in the winter, when it's cold, it turns transparent to that same infrared light, letting all that nice sun-warmed heat inside. And it's all passive. It happens automatically. Think of the energy savings. And for our final superpower, self-cleaning surfaces. This is all thanks to a principle called superhydrophobicity. Yeah, it's a mouthful, but you've seen it on lotus leaves in nature. It's when water, instead of spreading out, beads up into these perfect little spheres and just rolls right off, picking up any dirt along the way. So how do we make glass do that? Well, with CVD, we can do a process called surface fluorination. We're essentially depositing a layer of special fluorine-based molecules right onto the glass. This completely changes the surface at a chemical level, making it incredibly non-stick for water. The result is that extreme water repellent effect. I mean, less cleaning, better visibility in the rain, it's a huge win. So when you put all of this together, you start to realize we are living in the middle of an invisible revolution, a total shift in how we design and build the world all around us. So the real question is, what's next? The big takeaway here is that chemical vapor deposition is so transformative because it's the ultimate tool for precision manufacturing. It lets us give amazing new abilities to old materials just by controlling their surface, atom by atom. It's powerful, it's incredibly versatile, and maybe its greatest strength of all is that it's a revolution you will never, ever see. From the very screen you're watching this on right now to the windows in the buildings where we live and work, this technology is already here. It's already shaping our reality. So the question isn't if it's going to change our future, it's how. And seeing what it can already do, what do you think we'll build with it next?